Brought to you by Connect.js, Atlanta's premier JavaScript conference. Sponsored in part by FeatherDirect. Need a mobile app? Contact us for your custom mobile solution.
Great, thanks. Okay, let's get on with it. So I'm going to talk about Git from the inside out, which is a slightly different title from the one I submitted. But we're going to be looking at the internals of Git, mostly in the .git repo, in the .git directory. So 2 months ago, I realized that I was really scared of Git, which is terrible because I use it every day and have done for many years. So I decided to figure out how it works properly, finally. And so I ran, a ton of Git commands and in repos and inspected what was going on inside the Git directory to try and figure out how it was going on. So it was a bit like science. I would run some commands, try and figure out what algorithms were being used to produce the results I was seeing inside the .git directory. And then I used what I learned to implement my own version of Git in JavaScript. I'll put up a link to that later if you want to check out the code. And so this talk is my attempt to explain the heart of Git. So looking at the core data structures, spending the whole time inside the .git directory. And I'm not going to cover implementation details. I think that'll be for a future talk, or edge cases. We're just going to look at the common commands that you run using Git every day and how they work under the hood. And I'll assume that you're familiar with the basics of using Git, so kind of committing, branching, pushing, and pulling, but just only familiar in the sense that you've ever used those. So let's get started. Let's talk about hashes. A hash is a way of taking a usually long piece of information and condensing it down to a short string. So this piece of information is, hello, my name is Mary. Thank you for having me at Connect.js. And this is what it hashes. It's not what it hashes to. It's just a long alphanumeric string, but whatever. Anyway, so the idea of hashes is to take a piece of information and condense it, but also uniquely identify it. So in theory, no other piece of information will produce this hash. And so the idea is if you have a particular hash and a piece of information hashes to it, you can be pretty damn sure that that really was the piece of information that produced that hash. Now, I'm going to use a convention in this talk because those hashes are usually pretty incomprehensible. It's hard to relate the information that they represent to the actual structure of the hash. So in this talk, then, any blob, and I'll talk about what blobs and trees and commits are in a second, but any blob will be indicated with a hash of b hyphen and then some description of what it contains. So a file that has Monday in it might be represented with a hash which is b hyphen Monday. Then any tree will be t hyphen whatever, and then any commit will be c hyphen whatever. Let's talk about the project we're going to use for all the examples. There's a Mary folder inside the temp directory, and there's a day file inside that, which has just the word Monday in it, and then there's a doc folder which has a file called readme inside it, which just says day of the week. So it's the world's worst project. Let's talk about objects, which is probably the core concept in Git. So here's a blob for the day file on Monday. So we're right inside the Git directory. So, and then inside that is an objects directory, and inside that is a file called b-monday, which just has the word Monday in it. So we've successfully stored the day file at the state it's in when we started our repo. Here's another blob. This one's for the readme file. Its content is day of the week, of course, and its hash is b-readme for blob, and then it's just the readme. Now here's a commit object. And a commit object has a bunch of things in it. And this is the commit for the Monday state of the repo. So when it's Monday today, it's just got Monday written in that day file. And so this commit object has a tree, we'll come back to that, a parent, we'll come back to that, a date, and a message. And the message is the message that you type in when you commit. So when you do git commit -m, like woohoo or whatever, then it would put woohoo in the message. Now here's a tree object. And this is the tree that represents the doc folder inside our repository. So remember that we've got a root of our repository, and then we've got a doc folder inside it which has the README inside it. So this tree just represents the doc part of that, the doc folder. So we can see that it's got a blob entry, which is of course the README entry. And what this tells us is that A, it's a blob, B, that blob is at the state of b-readme, i.e. it's just whatever we stored with our readme blob, and then its name in the real repo is readme, okay, because obviously the name of the object in the database is b-readme. So that's the tree for the doc folder. Now we need a tree for the whole repository. So a tree, like I say, represents just one directory. It doesn't represent the subdirectories in any other way other than pointing at other trees. So here's the tree for the repository. Now, so we've got the top line has the blob in it for the day file at the bmonday hash. And then the second line is just a pointer to the doc tree that we saw a second ago. So let's just look at all those together. So those two trees relate to each other because the one at the bottom points at the one just above it. Then we've got the commit object, which we can see has a tree of t-monday. So that commit object is pointing at the tree for the root repo. We'll see a better diagram for this in a second. And then we've got our two data files that we actually care about. Now let's do another commit. So now it's Tuesday, so I've written Tuesday into the day file, and I've done a commit. So now there's been a blob created to represent the day file on Tuesday. There's been a new commit created, of course. Now we understand this a little better because tree is t-Tuesday for the tree that we haven't created yet, but we're about to. Parent is cmonday because that's the parent of this commit, the commit we did a second ago. Then we've got a date and a message. And then finally, we need one more tree to complete this, and that's a tree that represents the new state of the repo on the Tuesday commit. So what's changed? Well, the day file has changed. And so because the day file changed, then the tree pointing at it has to change too. So you can see that now that top line reads b-Tuesday, okay, whereas it's b-Monday a second ago, right? Whereas the doc folder is completely unchanged, and so that can just carry on living. And so we'll actually share that object, which we'll see in a second. So there's all the objects together. Here's a better representation of how they relate to each other. So if you look at the top right here, then we've got the Monday commit. And you can see that it points at the tree that represents the whole state of the root of the repo, right? And then it's got the day file and then the doc folder. Now, the doc folder has its own tree, of course, which just has the README in it. And then each of those point at their necessary blobs. So this top tree points at the Monday blob for the day file, which remember is in the root of the repo, whereas the tree for the doc folder points at the blob for the README. Okay, so these five objects up here represent that first commit. Now let's look at the second commit down here. So this is the Tuesday commit. It's pointing at its parent, which is the Monday commit, but it's also pointing at the tree that represents the state of the repo on Tuesday. Now we need a tree to represent that, of course. Now we've got b-Tuesday instead of b-Monday here, and then of course it's pointing at the new blob. But notice how it shares the structures from the previous commit. So it points at the doc folder tree to just share that object, because there's no need to create a new one because it didn't change. And by extension, it can share the README blob too. So this is something that's super cool about Git, I think, this kind of information sharing. And also, I think this is one of the most beautiful parts of Git as well. There's many beautiful parts, actually. But this is one of the most beautiful parts, because so often when people show Git and how it works, then they'll show a commit graph, which would just be these two items on the right here, the commits. And then they'll show some sort of list of blobs and trees or whatever, or maybe trees just on their own. And so they'll kind of separate the commit graph from the state of the repository at any one commit. Whereas what we can see from this diagram is that actually it's all entangled together. So we've got the relationship of the repository as it changed through time here on these two commits. But we've also got the objects relating to each other to describe the structure at any one moment. So we've got the data, the structure, the history, like that. It's so beautiful, I think. Yeah. Let's talk about building a commit in detail. So this is our state after our first commit. So this is the whole repo. So we've got the Mary folder up there, then we've got the working copy, which is just our data that we actually care about, sort of above the water, if you like. And then we go down into the depths of the .git folder down here. So we're on Monday, day of the week, README. That's not going to change for the whole of this talk. Now we've got this new mysterious file head, we've got this other file master, and then we've got the commit here. We're familiar with this commit object. So at this point, then what can we tell about the state of the repo? Well, number one, there's master. Now, if you ever use Git, then master's familiar. It's the branch that you do all of your commits to by default. And we can see that the master branch is pointing at the c-monday commit, which makes sense, right? Because that's the commit we just did. So that tells us that as far as master's concerned, it's Monday. However, slightly differently, then we've got this head file. And this is another state of the repo piece of information. But it tells us that as far as the repo is concerned, it's on master, right? So this tells us what commit master's on. This tells us what branch we're on, right? So if we want to figure out what the state of our repo is at any one moment, you just look at the head file, you find a branch name, you then look up that branch, and you find a commit. So that tells you you're on the Monday commit. Is this sort of like making sense? Yeah, great. Okay, so that's our state on Monday, though. So we're going to walk through doing the Tuesday commit step by step. So I changed day to read Tuesday now. So I've just typed that into the file, just actually doing some real work. Then head is the same. Of course, nothing else has changed inside the Git repo. But let's look at this index. So the index is another super important file in Git. Again, it's a flat file. You can just cat it. It's totally human readable, not scary at all. And the index represents every file we care about in our repository. So we can see we've got two entries. We've got one for the day file and one for the readme file, which makes sense, right? Because those are the only two files in our repo that we care about. This is the index from Monday, though. So we can see that the day file says b-Monday for our hash for the blob for Monday, and then the readme hash is there too. Now, but we've made a change to the repo, so we need to update the index to tell it about that change, right? So the index is both a state of, okay, these are the files I care about, but it's also, hey, this is the state of the repo that I would like to turn into a commit. So to update the index with our change to Tuesday, then we just do git add day, okay? So the day file is the one that has Tuesday in it. We do git add day to add it. Now that has two effects. Number one, let's start down at the bottom. It creates a new blob that represents day on Tuesday, okay? So we've successfully stored our data, which is nice. And we also update the index to say like, hey, it's not Monday anymore, it's now Tuesday. So that used to say day b-Monday. It now says day b-Tuesday to say to the index, hey, this is the stuff we'd like to commit. Now we call commit. So we do git commit. I'm so sorry, that's off the screen. Let me just go into, how does this work? Oh yeah. Okay, sorry about this, I have to say in this view, I hope that's all right. Let's just not spoil the surprise. Cool. Okay, so you can see that, right? Great. So we're going to do git commit -m Tuesday. Now let's take this commit step by step. So we're going to break it down into two steps. First of all, thinking about the trees. So we know we're going to have to make some trees because the day file changed. So we make that tree based on the index. How do we make that tree? Well, it's actually pretty simple. You take the index, which notice is a linear data structure, and you turn it into a tree-like data structure. So it's linear because it's just a list of files, but really, this is representing a directory tree, right? So a whole tree of directories where you've got directories going into directories. So how do we do that? Well, we just basically break it up into a tree where each level is a new directory, okay? Once we've got that tree that represents the state of the repo, i.e. both where all the information is and what that information is at the moment, i.e. it's Tuesday, then we can turn that into a set of tree objects. Now, we'll only need to create one tree. So we start at the top, we start with the root, and we say, oh, okay, well, inside my tree, I found a day file that's at bTuesday, so I'll add a line for that. And now I found this doc folder, so I'll add a line for that. But I can't actually write that line yet because I need to recurse in and create the underlying tree, which is the tree for the doc folder, right? Now, the good news is we've already created that tree, so we just go go into we will actually create it, find it's already there, not bother writing it, produce a hash for it, and then plug that hash directly in there. So t-doc represents that tree for the doc folder. Is that making sense? Seeing some worried faces. Anyone got a question about that? Happy to talk about it? Well, I'm going to re-explain it because your faces look worried. So we're trying to create the set of trees that will represent the structure of our entire repo, right, on Tuesday. Now, we've already got the set of trees for Monday, right? So that's 2 trees. It's a tree for the root, where it's Monday for the day file, and then the tree for the doc file. And then we've got another tree for the doc folder. We're trying to create the tree for Tuesday. Now, the doc folder hasn't changed, so we can just take that tree and reuse it, right? But the root directory has changed because it's now got Tuesday in the day file, right? So we need to remake this tree here. We need to make a new version of it and plug that in on a separate hash. And so we write the line for Tuesday. That's easy. We then find the doc folder, go and look for all the files that are inside that doc folder. We produce a tree for that. Now, that tree, as it happens, we've already stored, so we can, I don't know, you could restore it if you wanted to, or you could just not bother. But you get back a hash that represents that tree for the doc folder, and you just plug that hash in there along with the real file name for that directory, okay? So now we've got our tree. Final step. Oh, no. Great. Final step is creating the commit object. Now, this is the relatively easy part. We just create a new object. It's got a tree pointing at Tuesday. It's got a parent of Monday, and a date and a message. Now, how do we come up with that parent? Because it's like, I mean, we know that it's going to be Monday, right? Because that's the last commit we did. But how does Git know? Well, it's pretty simple. It basically goes to the head and says, okay, well, what state is this branch, is this repository in? It finds master. It's like, okay, well, I'll go and look up master. Now, that master would have said C-Monday a second ago because we were on the Monday commit. So it takes that commit as the state of the current state of the repo and then just plugs that directly in to the parent on that commit. Okay? So just to reiterate, master was on C-Monday, but head is pointing at master. So there's this kind of level of indirection. So head and master are 2 refs. And you can have basically broadly 2 types of ref. A concrete ref, which is something like master, which is a real branch which just points at a particular commit right now. But then you can have a symbolic ref like head, which is kind of changes what it points at from time to time, but always represents the state of the repo at any particular one moment. So if you want to figure out the state of the repo, you go to head, find a branch usually, and then you find a commit inside that master file there. Okay? So that's how we get the parent to be Monday. Let's just ram this home with a commit graph. So this is the state of our repo at the moment. So we can see that we've got the C Tuesday commit with a parent of C Monday, and we've got the master branch pointing at C Tuesday, and we've got the head pointing at master, okay? Great. Now let's talk about checkout. So this is our current repo state. We've got the day file reads Tuesday, we're on master, and master is pointed at C-Tuesday commit, okay? I run the command git checkout C-Tuesday, which is kind of weird, because normally when you run checkout, you pass in a branch, right? So what the hell's going on? Well, I've just decided to check out a commit, and we'll talk about what the ramifications are of that in a second. But this is also double weird, because we had master checked out, right? Which means that master was pointed at C Tuesday, so we're actually checking out the same content, but in a different way, which is weird. So we were on master, which was pointing at C-Tuesday, but now we're just checking out C-Tuesday directly. What's the point of that? Well, the point is to illustrate a detached head, and that's the state we're in now, right? So a detached head is where instead of pointing at a branch, then head points at a specific commit, right? Just like this, just up here, okay? So what are the ramifications of that? Well, what checkout does is A, it takes whatever you put here and plugs it directly into head, as long as it's valid. And then B, it will update the working copy to reflect the state of that commit, whatever that commit is. Now, the state of that commit is actually just exactly what we've already got checked out, so there's no need to check out a new working, to make any changes to the working copy. So we're in the detached head state. Now, let's just see what that looks like in the commit graph again. So we were in the situation where head was pointing at master, but now head is pointing directly at C Tuesday. So this is a detached head. Now let's set day to Wednesday, just typing it in again, just doing some real work finally. And what's the effect of that? Well, almost nothing except that the day file changes to Wednesday. Now let's commit that change, right? So we've made a new commit, we've gone through the details of that, we don't need to drag ourselves through all of that nightmare again. Now, head has changed to C-Wednesday, which makes sense, right? Because the parent of this commit was Tuesday, now we're on the Wednesday commit, so we'll just plug the commit we just created directly into head, which is to say we stay in the detached head state even if we carry on committing, right? So this is why people find detached heads kind of scary, I think, because you're doing real work, but you're not on a branch, and so you could easily lose it. Or rather, you won't lose it, but you'll lose track of it. So notice that master is still on C-Tuesday as well. Okay, so let's look at the commit graph again. So we've got this new C Wednesday commit, which points at C Tuesday as its parent. Master's still pointing at C Tuesday, and head is pointing directly at C Wednesday. How do we get out of this situation? Well, we can just branch. So we've done some useful work. We've made Wednesday, the Wednesday commit, which is great. But we need to point a branch at it so that we can save it away. So we just do git branch other. So what branch does is it just creates a branch. It doesn't check anything out or anything weird. It just creates a branch. And that's super simple. All it does is creates a new file inside ref/heads called other, which is the name of the branch we wanted to create, and points it at whatever head was pointing at, right? So head was pointing at C Wednesday, so other points at C Wednesday. Okay? So we've saved away our work now because look, the commit graph is now looking a bit less scary because we've got other pointed at C-Wednesday. Okay? Head is still directly pointed at C-Wednesday, which means we're still in a detached head state. But that's okay, we can recover from that pretty easily by just running git checkout other. Easy peasy. So now that we run git checkout other, the effect of that is, as we know, to update the working copy. No point doing that, we've already done it, we're already on C Wednesday anyway, so there's no need to change any of our actual files. But now head is pointed, we just update head to point at the other branch. Okay? So we've rescued ourselves from our detached head state. This is our commit graph. We've now got head pointed safely at other, everything's okay. So now let's get back on master, and remember that master was in Tuesday, and so we're back, it's now Tuesday as far as the world is concerned, and we're on master there. So just to reiterate that, head is pointed at master, which means we're on master, and master is pointed at Tuesday. Now let's commit the Thursday commit. So we type in Thursday into the day file, we commit that, so now head is still on master, of course, and master is pointed at C-Thursday. This is the commit graph, just to really ram the point home. Note that C Thursday is pointed at C Tuesday, so we kind of missed out Wednesday, but that's okay. And then C Wednesday is pointed at C Tuesday. It would be perfectly possible to resolve this situation and bring us back into a normal set of days of the week, but we're not going to do that in this talk actually, but whatever. So it's Thursday, master's pointed at Thursday, head's pointed at master. Let's talk about collaboration. We'll start with fetch, which is not that commonly used, but actually is used all the time because it's part of another command, which we'll get to in a second. So what I'm going to do is I'm going to make a new repo, right? And I'm just going to use the command cp to do that. So cp is a Unix command which will copy a thing to another thing. So in this case, we're copying a directory Mary to a new directory Sam. Now, that's all right. So I copied Mary to a new directory Sam. Now this is nothing to do with Git, absolutely nothing to do with Git. I've just copied a directory, there's nothing to panic about here. On the left we've got Mary, where it's Thursday, and on the right we've got Sam, it's also Thursday. And note that it's also copied the Git directory, of course. So this is one of the super, super cool things about Git, is that you can just take a repo and copy it to somewhere else, and bam, everything just works. So now let's commit Friday to Sam, not Mary, that's crucial. So we're working on the right here. We're working on the right. So I wrote Friday into the day file, and then I committed, and so now master is pointed at C Friday. So this is the state we're in. On the left, everything is as we left it because there's no communication at all between these repos. They're just two separate folders on some computer somewhere. So on the left, then head is pointed at master, and master is pointed at Thursday. On the right, then head is pointed at master, but master is pointed at Friday. So it's Friday for Sam, Thursday for Mary. Now let's get these two repositories talking to each other. So I'm going to do git remote add Sam some file path, right? So let's unpack that. What does that mean? Well, remote is what we call a repository that is a bit like our repository. So I've said, I'm in Mary now, so on the left here. I've said, okay, hey Git, there's this repository that's kind of like Mary that is, I would like to call Sam, and lives at /temp/Sam. Now, you don't have to use HTTP to do transfers between different repositories in Git. You can totally just use file paths, which is super cool. So the effect of this is just to update the config file, another file we haven't met yet, but again, super, super cool, not scary. It's just a flat file. It lives inside the .git directory. And it has a list of config stuff, a ton of stuff, but the thing we care about is that we've added a remote called Sam at this URL, or at this file path, rather. Okay? So that tells Git, hey, Sam lives here. Now we're going to do git fetch. Now, don't be afraid of this diagram. There's a lot going on, but we're going to walk through it step by step together. So I'm going to call git fetch. And fetch says, hey, I'd like to get some work from another repository and bring it into my repository. Okay? So, and the repository in question is Sam, and I only care about the master branch. I don't want to get bogged down in the other branch or whatever. I just want master. Okay? So there's a few things that happen as a result of this. First of all, we know, because we committed Friday to Sam, that there's 3 new objects that are in Sam's objects directory: a commit object, a tree object, and a blob object. So first we just copy those all across to our Mary repository. That's the first effect. Super easy. Now, notice that there's no distinction between my objects and other people's objects. It's just all the same. Second, we say, okay, well, Mary cares about master because she said that in her git fetch command. So I better go and get the state of master, which is C Friday commit, and somehow tell Mary about it, right? So how does that work? Well, we don't want to just jam C Friday in some crazy way into our local master here. We don't just want to put it in there, because that would start messing around with Mary's perceived state of the world. So we have this other subdirectory of refs called remotes, right? Makes sense. And then inside there is a directory called Sam, and inside there's a file called master, which is updated to say C Friday. So we've pulled that work over. So imagine you're getting on a plane, and you've got a ton of work to do that's based off Sam's work. And there's no Wi-Fi. You could do a fetch, and you wouldn't start integrating any of Sam's work into your work. You would just put it, for safekeeping, within your own repository. And then you could get on that plane, disconnect it from the internet, and everything would be okay. And you could use all of Sam's work, and everything would be fine. So we've now got C Friday, so we know what the state of Sam's master branch is inside our own repository. There's one final change that the fetch command makes, and that's this fetch head, which is another symbolic ref, just like head. And fetch head just represents the stuff that you most recently fetched. That's it. Okay? So what did we most recently fetch? Well, Sam/master. So Sam is the remote, master is the branch. So all that says to our Git repository is, hey, FYI, this is the stuff we fetched in the most recently. So how do we integrate this work with our work? Well, we can run git merge fetch head, right? Now, we haven't talked about merge at all, and we're not going to talk about it much. Merges are pretty relatively involved. It's pretty okay, but it's relatively involved. I'm still implementing it, so I certainly can't talk about it authoritatively. at all. But what git merge does is it says, hey, take what's in fetch head, which is just the state of Sam master, which we know is just the C Friday commit, and please merge it into my work. Now, that merge is actually super easy because the parent, remember, of C Friday is C Thursday, which is the commit that Mary is on. And so you can just walk forwards in the commit graph and you just be on C Friday. There's actually no merge that happens, so that's all good. But like I said, we're not going to talk about the details of merge. So just accept that we're now on C Friday. So you can see that reflected by the fact that my master, Mary's master, now points at C Friday. Okay? So we've successfully brought in Sam's work into our repository. So as far as Mary is concerned, it's now Friday, which is awesome. Let's talk about pull. Pull is the command that you would much more often use to do precisely the same thing. So pull just combines fetch with merge fetch head. Okay? So if I had run, instead of doing all of that, like jumping around with fetch and merge fetch head, if I just said git pull Sam master, it would have had exactly the same effect. Let's talk about push. I commit C Saturday to Mary. So we're back on Mary over here now. So Sam is now behind the times. So I write C Saturday into the day file, I commit it, and so now master is pointed at C Saturday. I then do git push Sam master. Now this is going to mostly fail, and I know mostly is a bit of an equivocation, but let's think about why it's going to fail. This is on recent versions of Git that it would fail. So first of all, what we want to do is we want to push Saturday to Sam, right? So first of all, we're going to have to push some objects. Now that bit's fine. That bit actually happens with the git push Sam master, so it's not a complete failure. And the reason it happens is because that's okay. Because we can just share objects and they can just all coexist together, because the chances of a collision are like, it's far more likely that a sea of frogs will suddenly burst into this room. So it's fine. So we can just take objects and just put them into other objects directories, and that just works. But there's problems that come after that. So first of all, let's think about what would happen if I were to effectively merge my Saturday with Sam's Friday. That would cause a meaningful change to his repository, right? Ending with his master pointing at C Saturday. Now, that could be a bit alarming for Sam. Maybe he's not ready for Saturday. And he could be in the middle of some changes, so now suddenly, bam, his master is changed to be Saturday. Even more terrifying, he could be working on some changes on his working copy, just typing them in, hasn't saved anything, hasn't run any git commands on them at all. And then suddenly, because effectively it's going to result in a checkout of that new work doing this push, then his in-progress changes will suddenly just get instantly replaced with my Saturday changes. So that's even worse, right? Because that doesn't work because Sam's repository is a working repo, right? It's a repo that he's actually doing work on. So that's why that push is just going to mostly fail. But let's think about pushing, because we do actually push all the time. So how does that work? Well, I'm going to create a new repo called hub, and I'm just going to create a new folder called hub inside the temp folder here. So we're on the right here. So this is no longer Sam, this is now hub, okay? I'm just going to say that again. This is no longer Sam, this is now hub, okay? And then I run git init -- bear inside there. And that creates a new Git repo, but it spews the whole of the contents of the .git folder into the root of the repo, which is to say there's no working copy. So this is not a working repo. This is just designed to store changes. So the reason I chose hub for the name of the repo is because I'm sure we can all think of a hubby type thing that works this way, right? So it's just the central repository for our changes. It's GitHub, right? So now I can happily push, I can add a remote quickly. So I just do git add remote hub and tell it where it is. That's exactly the same. We've seen that before. And now I can do git push hub master. And so this will share my changes perfectly fine, and this command will succeed. So let's think about what's going to happen. It's going to take all my objects and put them in the hub repository. It's going to take Saturday, which is my latest commit, and make the commit on the master on hub point at Saturday as well. And then it's going to point head at master too. Notice there's no working copy changes because there is no working copy. So that does push, and that's how that works. And that's what happens when you, I expect, when you push to GitHub. So that's all the stuff I'm going to talk about. where can you go from here? So my idea has been to sort of show what's going on inside the .git repo. How can you find out more? Because I'm sure this talk leaves a ton of questions unanswered. We ignored a ton of commands, especially merge, which is super important. And there's also, we didn't really walk through any of the edge cases of any of these commands. So that's why I wanted to leave a ton of time for questions, ideally. So how can you explore more on your own, real quick? First of all, if you want, you can check out my implementation of Git. It's 1,000 lines of JavaScript. It's designed to be super readable. I'm still working on merge. I'm going to finish that in the next week or so, and then it's going to be done. I'm also going to release an annotated version of the source, which will have very heavy code comments in it, probably in the next month or so. So you can check that out if you want to. Or you can try and teach someone else how Git works. I find that whenever someone asks me a question about how something works, I say, oh yeah, that's, and then we start working through it, and they ask some great questions, and I realize that I don't understand some components, so we can just figure it out together. So I just find trying to teach other people stuff shows you how little you know, and then you learn more, and that's great. Or you can make a Git repo and start running some commands, fucking around with it, and then just seeing what's going on inside the .git directory. It's really not so scary, as I hope I've shown. Or you can write your own Git. Highly recommend that. It's amazing. I found that every time I read a bunch about Git, read a bunch of documentation, I'd be like, yep, I can implement checkout, no problem. I'd sit down, start typing, and realize that there was some edge case I didn't understand, or some particular case, or whatever. And so I found that it cemented my understanding of Git way more. It was awesome. So thanks so much for listening. It's really nice of you, and I will take questions until lunch.
So when you said git add SAM, or sorry, git push SAM masters, that would fail, but git push hub master worked, we lost you there. Why would the same work? Doesn't that work the same way that the first one did?
Sure, that's a great question. So the question is, why didn't it work when I did git push SAM master, but did work when I did git push hub master? And the answer is because hub is a bare repo, which is to say it doesn't have a working copy, and it's not expected to have anyone making any meaningful changes in it. So it's effectively like a sort of clearinghouse where you can just, it accepts that it can just have anything shoved into it that merges okay, and it will just work as long as there hasn't been a divergence in the history, but I haven't got time to talk about that. But so effectively that's like GitHub. So you can, people view bare repository as their sort of playground to do whatever they want in. So they can just say, hey, hub, this is now the state of the world. Get on with it. Okay?
And was the dash bare command setting that repo to know that it's not a working copy?
Precisely, exactly, yeah. Any other questions? Yep.
Speak a little bit about what blobs are made of? Like,
Of course, yeah, that's a great question. So blobs are amazing. They're just your data. They're just inside a file in another place, basically. They are compressed by default, but you can actually turn compression off, which I highly recommend if you want to go poking around inside a .git directory. It's very easy to turn compression off, and then everything's just effectively stored as a flat file, and you can see all of your stuff in the objects directory.
is it just like the div patches, or is it the entire file?
Great question. So the question is, does Git store diffs inside the objects directory, or does it store the full content? It stores the full content, and the reason that's tenable is that actually commit to commit, most files don't change, and so the graph can just point to all the old stuff, and then make a couple of new blobs, or maybe a couple of new trees for the new stuff, point at that, but most things haven't changed. So this means that there's no need for diffing from commit to commit. Now you can, of course, run diffs on demand inside by running git diff or whatever, but that's a different matter. The whole full content is stored every time.
So along those lines then, sometimes when you're doing some more complex things, like say you're renaming a file, and then you're making changes to that file, sometimes if you don't do a git add right after you do a rename and make those changes, sometimes git can't really guess that, oh, you did a renaming, you changed some of the file contents. How does it keep track of what the most, you know, when you're looking back into it, how does it keep track of which thing was the most likely sequence of steps as opposed to producing this awful div?
Sure, so great question. So the question is, Git correctly identifies sometimes that you've renamed a file, or so you've moved a file, rather than you've created a new file that happens to have the same content in it. The way it does that, I believe, is by a series of heuristics. And so I expect that the distance of time in terms of the number of changes since that move happened probably plays into that. I haven't actually looked into the details of it, so I can't talk about it at all, but I believe it's very much heuristic rather than like some sort of hard and fast rule it uses.
Well, if you just move the file, you have the same hash.
Absolutely. So I think that link starts to break down, but like I say, I don't know the details, so yeah, I'm sure. Any other questions? Yep.
Yeah, when you say you write your own Git, like if you want to go down that path, where would you even start? Would you start with like the original source, or is there a spec that exists or something like that?
Sure. So that's a cool question. So great question. So where I started was I just started with init, which is relatively easy to implement because you've just got to make a bunch of files and folders inside a repository, and so that was okay. And then I started with add, and I just realized I didn't understand what the hell was going on, and so I just started playing around in Git repos, trying to essentially do science to figure out what add was doing. I also read the docs, I read some articles about Git. I found that unfortunately, I don't read C, and so the Git source is in C, so I did actually look at it a couple of times for small things, but for larger inferences about how it worked, it was a bit of a mystery to me, I'm afraid. But definitely reading the source if you read C would be fantastic, I think. Yeah. Any other questions? Great, okay, thanks so much. Happy to talk about Git anytime.